In this lecture, we'll be continuing on with our survey of the periodic table, and now we're moving into the P block, and we're going to be looking at groups 13 and 14, also known as 3A and 4A, and you can also call them the boron family and the carbon family for the top element in each group. Okay, so starting with the boron family, group 13 or 3A, here are the elements: boron, aluminum, gallium, indium, and thallium. Okay, and their electron configurations, right? What you'll note about that is they all have S2P1 configurations, right? Just different in different principal quantum numbers. And how they look, they all sort of look a little bit metallic in a way, but definitely aluminum, gallium, and indium are the ones that look the most metallic, probably. Thallium's a little bit different looking, even though it's the last element and lowest element in the group, should be the most metallic, but it just kind of maybe doesn't look like that in the picture. Okay. Right. So there's some differing properties among this group due to that metal-nonmetal line bisecting the group. If you remember, there's that line right below boron, between boron and aluminum. That would be the metal-nonmetal line. So there are going to be some different properties there. All right. So for this group and some others as we move along, the effective nuclear charge increases for the larger elements, the ones that are further down in the group, and that's due to poor shielding by the D and F electrons. So we talked about this a little bit when we were talking about transition metals and intertransition metals, but here it kind of manifests itself. So the larger 3A elements have smaller atomic radii and larger ionization energies and electronegativities than would be expected, and we'll see that when we look at that family portrait slide at the end of this discussion of this group. Right, so these properties are going to influence the physical and chemical behavior of these elements. So what are some features? Well, the larger group 3A elements exhibit multiple oxidation states. Okay, they can lose only the p electron and be a +1 state, or they can lose the p electron and the two s electrons and be a +3 state. So aluminum, being higher up in that group, is always found in the +3 oxidation state. But some of the elements lower in that group can be either +1 or +3. The lower oxidation state, the +1 state, becomes increasingly prominent down the group, in that sense that those s electrons form an inert pair, and we talked about that previously, how when the effective nuclear charge increases, because those D and F electrons aren't shielding very much, those S electrons now are held tighter and they aren't let go as easy, and that's what we refer to as an inert pair. Oxides of the elements in the lower oxidation state are more basic than oxides in the higher oxidation state. So the oxide formed with the +1 oxidation state in this group is going to be more basic than the oxide formed with the +3 oxidation state. Okay. And if we just in general talk about acid-base behavior of oxides, main group metals form ionic oxides, which are basic in aqueous solution. Main group nonmetals form covalent oxides, which are acidic in aqueous solution. Okay, so if you have a main group metal, that's going to form ionic compounds with oxygen, and a main group nonmetal forms covalent compounds. All right, and that's why we discuss them and term them as basic or acidic. Okay. Some metals and metalloids and that's kind of where we are. We're right around in this group. There's that metal nonmetal line, so we're right there with the metalloids. They have oxides that have amphoteric behavior, and amphoteric means they can act as a base or an acid. So here, aluminum oxide, when it reacts with an acid like HCl, right, it can act like a base. When it reacts with sodium hydroxide, it can act as an acid would. So let's look at some of these elements individually. The top element in the group, boron, what the group or family is named for, has a very interesting chemistry. All of its compounds are covalent. Okay, so it's a nonmetal. You can consider it like a nonmetal, and it makes covalent compounds. And it forms network covalent compounds with other elements. And so this is sort of like carbon, where we can have a network of covalent bonds. But some of these bonds in boron are quite interesting. If you remember back from when we talked about Lewis structures, boron is electron deficient in compounds, or it can be. So things like BF3, boron does not have to have a full octet. And because of this, it acts as a Lewis acid because it can accept electron pairs and form adducts. The really interesting bond that boron can form, it's called a bridge bond. And this is a bond where one pair of electrons is shared between three atoms. So you can think of it as like a 3-center 2-electron bond. And it's very common between boron and hydrogen. Right, so you have, this is a molecule called diborane. You have 2 boron atoms and 6 hydrogens, and it's bonded together in this network. Right, these are normal bonds on the side, these hydrogens on the side. Right, they're just one bond, 2 electrons shared between 1 hydrogen and 1 boron. The ones in the middle, and it might look kind of weird, right, because it's hydrogen here, and you have 2 bonds going to it, which, you know, normally we'd think that can't happen, right? Hydrogen can only have 1 bond. But what this is it's actually these bonds, these 2 bonds here, they are actually 2 electrons shared between these 2 bonds, right? And so this is what we call the bridge bond, or 3-center 2-electron bond. And if you look at the overlap picture, the hybrid orbitals here, it's 2 sp3 hybrid orbitals from each boron overlapping together with that s atomic orbital from hydrogen. So you have this sort of triple overlap where now 2 electrons can be shared between those. Okay, so this is a very interesting and unique type of bonding in boron compounds, or also referred to as boranes if it's a boron hydrogen network. So here we have some other more complex boranes. We have B12 and B5H9. So you can see that it can get these multi-center sharing bonds can get very complex. Right? And so a man named William Lipscomb actually won the 1976 Nobel Prize for research on bonding in boron compounds. And I've showed this slide before. So if you were in my class first quarter, you probably saw this in a lecture about, what was it about? About Linus Pauling and valence bond theory. Okay? So I've kind of told this joke before, but might look familiar. But so William Lipscomb won the Nobel Prize in 1976 for research in these compounds. Why is that important? Well, Linus Pauling was actually an advisor to William Lipscomb. He worked in the lab of Linus Pauling. And if you remember Linus Pauling, before I go on, Linus Pauling won the Nobel Prize for his work in valence bond theory and elucidating the nature of the chemical bond and electronegativities. So he was, and also involved in quantum theory. Right. So he taught William Lipscomb. William Lipscomb had a graduate student, Gareth Eaton. And Gareth Eaton is actually a professor here at the University of Denver. He works in electron paramagnetic resonance, very highly thought of in the field. And one of the graduate students he had in his lab over the years was me. So it's easy to see, all these Nobel Prize winners and very smart people, and where the disconnect, you can lose this after a single step, right? Right. And then, of course, there's you. You're actually not very far off, not very far removed from some very important people in the field of chemistry. Right. Boron can make many different compounds and some that are very useful in industry. One of them is termed borax, okay, and it's labeled on this box as a detergent booster, but there are many different uses for borax. Right. And here are some of the compounds boron forms with oxygen. Borax would be one of them. Okay, so it, again, can form these sort of very complex covalent compounds with hydrogen and with oxygen. And one of the main uses for boron in something that we've talked about in this class, nuclear chemistry, nuclear reactors, these control rods that are labeled here as neutron catchers, they have boron compounds in them that they're made up of. And why that's important? Well, boron's a very good neutron catcher. It can absorb neutrons and not be radioactive, not turn into something that's super radioactive. And why that's important? Well, you need these control rods to go in between your uranium and limit the number of neutrons that are passing between the uranium to try to control the level of nuclear fission that's occurring, right? And when there's a problem with these control rods, right, if they get all pulled out and this is allowed to kind of go uncontrolled, that's when you get a chain reaction, an uncontrolled chain reaction, which then would lead to meltdown of the reactor. Well, there are some other elements in this group that form sort of similar bonding. They're not the same with 3 centers and 2 shared electrons, but they have the same look and same geometry as these bridge bonds in diborane. And aluminum is one of those. So aluminum can form these sort of strange covalent dimers with chlorine here, right? And that's a little bit strange too, because aluminum, we kind of think of it as metal, right? It has the physical properties of a metal, but these halides exist as covalent dimers, so it can actually form covalent bonds, which is unique. But there's this diagonal relationship between beryllium, which is in group 2, and aluminum in group 3A. Right, that's that diagonal relationship. Both form oxoanions in a strong base, right? So they combine with OH minus and form these anions. Both have bridge bonds in their hydrides and chlorides. So that bridge bond that we saw previous slide. The oxides of both beryllium and aluminum, the coatings on the outside of them are impervious to water, right? They form these oxides in air, and that's one of the reasons why aluminum is so thought of as being passive or non-reactive or can't rust is because it forms oxides on its surface, and these are impervious to water. The oxides are amphoteric, meaning they could act like a base or an acid, and they're both extremely hard with high melting points, the oxides of the two metals. Some aluminum and all beryllium compounds have significant covalent character. Right? So that's another similarity between the two, even though they're not in the same group. Right? There is this diagonal relationship. Right? So if we look at the family portrait of boron, right, we have the sizes, atomic sizes, right, and you'll see again these aren't really increasing as we go down. Between like indium and thallium here, you don't get as big of an increase in size as you would expect. And remember how we said the ions formed with the group, the elements lower in the group, will tend to favor that low oxidation state where it only loses one p electron. And so that's shown here with thallium. It's a +1 state, where all these others are shown as the +3 state. Okay, electronegativities, right? They start to go down, but then they increase as you go further down that group, which you wouldn't not really expect that. And the first ionization energy sort of does that as well here, at least at the end, right? And that's again that inert pair effect. Some of the reactions with these elements, we saw the alkaline metal in the group 2 metals. They can react with water, especially group 1 metals. These group 3A, they react very slowly and sometimes not at all with water. And it tends to have to be either hot water or in the form of steam, right? So you have to add some energy into this. It can't just be room temperature tap water. Right, when strongly heated in pure oxygen, all members form oxides, right? And all members reduce halogens. So they get oxidized and they reduce the halogens. If we look at the bond type, again, most of the bonding in this group would be classified as metallic bonding, although remember aluminum does form some covalent bonding. And then boron is that covalent network bonding that we see in other elements like carbon that's fairly unique. Okay, speaking of carbon, we're moving on to group 4A, which was the carbon family. Right, shown here, right, diamond, carbon in the form of diamond is quite unique. It's a very clear crystal. Silicon, it's sort of, grayish brown, almost looks like a rock. Nothing too spectacular about that. Germanium, now you're getting a little bit more metallic looking. And then finally, tin and lead are metals, right? If I said tin, something made out of tin to you, or even lead, I think you'd all sort of have this picture in your mind that those are metals. Okay. Each element in this group has that electron configuration, valence electron configuration of s2p2, right? There are differing properties among this group due to that metal-non-metal line again. Sort of a common theme we have. We're going to introduce a term, and this is specifically going to be used in this class for the examples of carbon, but this term exists for other elements. It's called allotropes. And what allotropes are different crystalline or molecular forms of the same element. So it's an element that can exist in multiple forms. And we'll explain that here in a second. One allotrope of a particular element is usually more stable than another at a particular temperature and pressure. Right? Carbon has several, right? And the big ones are graphite and diamond. So those are examples of allotropes. But the other one is known as fullerenes. And fullerenes, we'll see a slide here in a second. Fullerenes are more complex, three-dimensional bonding of carbon with itself. And again, this is all element, right? These are carbon making a covalent network bond with itself, right? Tin actually has allotropes too. It has two, white beta tin or gray alpha tin. Although, we really don't talk about those as much in this class. But that's an example of how other elements have allotropes as well. If we look at the phase diagram of carbon, right, we have solid carbon. It can exist, and this is showing those two allotropes, the two most common ones, diamond and graphite. So diamond really takes higher pressures or temperatures to form diamond over graphite. So on Earth, right, graphite is really the more common allotrope. It takes higher pressures and temperatures that are found deeper within the Earth to make diamond. And then again, you have the liquid and the gas at much higher temperatures and lower pressures. The other allotrope we mentioned are fullerenes, and it's short for Buckminster fullerene. Buckminster is the person that discovered these compounds. Right. So we have here a buckyball. Right. That's the Buckminster fullerene that was first discovered. C60. So there's 60 carbons here, and it looks kind of like a soccer ball. Right. It's kind of an alternating pattern of hexagons and pentagons. There was also, after that was discovered, people started playing around with these and trying to develop others. Nanotubes, so carbon is sort of in this shape, but it's open-ended, so it makes a tube-like shape. Okay? And then you can also have these planes, like graphene planes, right? So these are really big in the field of materials chemistry because you can design these. They're very, very small particles, and they have some very unique properties because of their relative small size, and they're used in a wide variety of fields. So bonding in this group, carbon, as we've talked about, forms really covalent bonds. Larger members of the group can form bonds with more ionic character. So as you go down that group, you can get an increasing ionic character in the bonds. Elements of this group also exhibit multiple oxidation states. The lower oxidation states become more predominant down the group. Lead and tin show more metallic character in their lower oxidation states. So the +2 oxidation state of tin and lead are white, crystalline solids, and they have higher melting points, so they're more ionic. Tin, the 4+ oxidation state here, so tin, chloride, and tin's in the +4 oxidation state, is actually volatile, and it's soluble in benzene. So it's a liquid, right? So not something that acts like it's ionic at all. Here's just a picture of that with both tin and lead. So the +2 oxidation state forming a chloride is ionic, and the +4 oxidation state forming a chloride is kind of like an oily liquid. Carbon is very important because of the type of bonding it can do, the vast amount of bonds it can form. And we have that whole class that some of you will take next year, organic chemistry, about this bonding. Okay, very wide variety of bonds it makes and wide variety of organic compounds. This process of carbon bonding to itself to form stable chains and branches and rings, that's referred to as catenation. And why carbon does that and not other members of this group that have the same electron configuration, it's because of carbon's relatively small size, right? The carbon-carbon bond becomes shorter, and it's short enough to allow effective side-to-side overlap of those unhybridized atomic p orbitals. And that's where it can form double bonds and triple bonds, where other elements further down this group just can't do that because the size of the elements is too big, and that makes the bonds too long to get the pi bonding. Right, here are three, this slide title, 3 of several million known organic compounds of carbon. Right, and you'll see, right, their carbon can form double bonds and triple bonds, whereas other things really can't, right, with the exception of oxygen and nitrogen. Other elements in that row, right, the larger ones can't do this type of bonding. That's acetonitrile, a solvent that's widely used in the lab. Lysine, that's an amino acid used in protein synthesis in cells. And then you have a polymer here. If you take this unit and this unit and stick them together and make a long chain of that becomes what's known as Kevlar, right? Something that's very strong, and bulletproof vests are made out of Kevlar, so it can make a very strong material out of this polymer. Okay. Carbon can also show up in inorganic compounds. So carbon bonds with oxygen to form what's known as carbonates, and metals, those carbonates are negatively charged, and they can be the counter ion in metals such as calcium. So calcium carbonate is abundant it would be a mineral that's in limestone, and so other carbonates are abundant in minerals. Right. Carbon forms 2 common gases, carbon monoxide and carbon dioxide. Right. They're molecular gases. Right. Other group members here form network covalent or ionic oxides. Okay, so this is a little bit different. Carbon forming these small molecular oxides that are gaseous. Carbon halides have major uses as solvents and structural plastics. Right, so Freon is an example of a refrigerant, although it probably really isn't used much anymore, but used to be used in air conditioning. And these PCBs can also be used as industrial solvents, or if you react them to bond together, they can make what are known as plastics or other structural polymers. Carbon's fairly unique in that it has an environmental cycle, and we'll talk about this as well when next lecture when we're talk about nitrogen. So those are the two that have, I'm sure other elements have them, but these are some of the more important ones, the 2 most important environmental cycles. Right, and what an environmental cycle is just the natural process which elements are continuously cycled in various forms between different regions of the Earth. Okay. Elements are cycled through physical, biological, and chemical pathways. The most important of these cycles from the perspective of us, living organisms, are carbon, nitrogen, and phosphorus. Okay, carbon appears in all three portions of the Earth's crust. Okay, elemental carbon occurs as diamond and graphite in the lithosphere. Carbon is a component of carbonate minerals, and carbon forms the basis of all organic substances on the surface of the Earth. Right, CO2 gas is found in the atmosphere, and it's found dissolved in all waters on the face of the Earth. Okay, so what the carbon cycle is, and what processes you have. It is a cycle, so it's like a circle. Doesn't really have a beginning or an end, but if we just pick one, and that would be the term fixation. So fixation is the process of converting a gaseous substance into a condensed form. Right? Through photosynthesis, plants use sunlight to fix the CO2 that's in the air into carbohydrates. Right? So you can think of carbohydrates as sort of as sugars. Okay? Animals eat the plants, so they ingest these carbohydrates. Right? So the carbon that was in the air is in the form of CO2 is now in a plant carbohydrate. An animal can ingest that from plants, and now they have that carbon in their systems. Right? All living organisms release CO2 by respiration and by decomposition. So, animals eat plants, they're breathing in air and breathing out CO2, so they're putting some of that carbon back in the atmosphere. And some of it goes into their structures, the carbohydrates, the proteins, the fats that they have in their system. Right? When they die through decomposition, that carbon goes back into the soil. Right? The portions of this carbon cycle are linked by the atmosphere. One link between oceans and air, and the other between land and air. Right? So here's what that looks like. Not going to need to know all these details in this class, but this just gives you kind of a picture of how this is working. Right? So you have atmospheric CO2, plants then take that in and fix it, and then animals, not really shown on this this chart here, is animals can take the carbon material from plants and use it themselves. Okay? And you have a gaseous element or molecule in atmosphere above liquid. There's going to be some of that gaseous element, or gaseous molecule, I should say, dissolving into that liquid. So there is this equilibrium between the amount in the atmosphere and the amount that's dissolved in all liquids. Okay. And it's really, with the man-made combustion of carbon and production of CO2, there's this natural cycle, right? Simply putting a little bit of CO2 in here, you can see that if that happens, well, plants can absorb it. It can absorb in the water. Shouldn't be that big of a deal. But when you have this constant input from humans, and if it gets large enough, you can kind of throw this whole thing out of whack, get much more in the atmosphere than there used to be, which means there's much more in the ocean surface. The amount, if the temperature increases much on the planet, you have what was once stored in the ocean now being released into the atmosphere, which makes the problem worse. So, again, not really something we'll go into the details of in this class, but if you're interested, that's all part of this carbon cycle. If we go down an element in the group, silicon, and highlight some of its chemistry, silicon can also form network covalent molecules, and it tends to do this with oxygen. Right? So, and it forms these repeating silicon-oxygen units, which are found in both silicates and silicones. Right? Silicate building unit is the orthosilicate grouping, which is silicon O4. right? And it has a tetrahedral arrangement. Silicate minerals are the dominant form of matter in non-living world. Maybe you don't really realize that, but this building block here is actually very prevalent. And it's included in clay and sand and actually even in some semi-precious stones. So it's in the ground, there's a ton of it. Silicone polymers are synthetic substances consisting of alternating silicon and oxygen atoms. They're used in a wide variety of applications. Right, here are the structures of some silicates. Right, you have just the basic silicate ion in zircon, and it's 1 silicon and 4 oxygens in that tetrahedral arrangement. These can be linked together via this sort of, not really a bridge bond, but kind of, right, between the oxygen on one and the silicon on another, right? So these can be stuck together, and you can get very complex arrangements of these, right? And quartz is an example of this. It's a 3-dimensional framework of silicate, right? So it makes this very nice crystal, but what it's made up of is essentially that building block, that silicate building block. Right, the family portrait for carbon, again, electronegativities, right, go down, but it's kind of flatten out, and at the end in lead kind of goes up, which again, wouldn't expect that. If you just follow the trend, it should keep going down. So these are higher than expected down here. And the ionization energies are a little bit higher than you would expect as well. The reactions in group 4. Group 4 elements are oxidized by halogens, right? So they reduce the halogens, much like group 3A does. +2 halides are more stable for tin and lead, right? Because they have multiple oxidation states for tin and lead, but the +2 halides are more stable than the +4. Elements are oxidized by O2. Oxides become more basic down the group. Hydrocarbons react with O2. So an example of that, methane CH4 reacts with O2 gas to form CO2 and water. This, if you remember, is a combustion reaction. So hydrocarbons, that's a very important reaction for hydrocarbons, is combustion. And actually, that's a reaction that we use inside of our cells when we're breaking down carbohydrates such as glucose. We're, in a sense, combusting them in our cells to get energy. Right, and silica is reduced to form elemental silicon. So you can reduce silica, which is silicon oxide, with carbon to form elemental silicon. Right, so that is our end of discussion of those two families. We will move on to group 5A and 6A next time.